I'm actually not quite sure I can promise Q code, but you'll see some Q code perhaps. Apologies for that. On behalf of Citadel Securities, thank you for being here. I hope you're having a good time. I will try to accelerate our path towards drink and food. This is me. I'm a senior developer at Citadel Securities, also a C++ enjoyer. Make of that what you will. So unlike the previous two presentations, mine may not be quite as useful, but hopefully equally interesting. This is basically going to be kind of a show and tell of two interesting projects that we did at Citadel Securities. And yeah, the first one is what we call QCPP, which is essentially a pure C++ from scratch implementation of a Q client library. We get true asynchronous communication. We have a Q data representation based on STL data structures. And we have direct conversion to and from IPC format from a variety of types, no intermediate K0 pointers necessary. So this is kind of a crazy thing to do. Like, why did we bother doing all this? There's a few reasons. One is familiarity. Citadel Securities is mainly a C++ shop. And we're making increasing use of Q. We have a lot of stuff that's built in Q, a lot of really good stuff, and we want to make it easier for people to connect to it and deal with it. And C++ is kind of the lingua franca there, so we wanted to make that as easy as possible. Efficiency, for example, I mentioned we can go directly to QIPC. Fewer data conversion hops is always good. Features, we can support true asynchronous in C++ via Boost asynchronous I/O. We have no restrictions on where you allocate in free memory. It's just normal C++ data structures. Also control. If we make bugs, we can fix them ourselves without much help. That's kind of a double-edged sword. Finally, the reason not listed on here is it was kind of fun to do. So how is this organized? There's really two kind of layers of the library. One is the core layer. This is basically the basic C++ data structures, mapping them to Q, and a few other things. The main one is sort of serialization. You can implement, you can basically give an override function and serialize any one of your types directly to Q, or deserialize directly from Q to your type without any sort of intermediate copying. This is quite useful. So for example, if you have a vector of structs, you can convert that directly to a table in the wire format, send it over to your ticker plant, and you're done. Quite nice, actually. On top of that, we built a few sort of common data formats that we can convert to and from Q. One is sort of our own one-to-one representation of any possible Q value, including things like compositions, lambdas, things like that. This is effectively a big STB variant. It's quite nice for C++ developers to be able to deal with it that way versus kind of opaque pointers that you usually get with Q. Again, we have direct serialization to and from STL. So if you have an STD map, a vector, or whatever, you can send it directly to Q, and the library knows what to do with it, and will sort of transparently send it over. This all works kind of recursively, so if you have, nested structures, it all gets converted to Q correctly. Again, very convenient. On top of that, we have sort of the communication layer. This implements the Q protocol. Again, very helpfully documented by KX on their website. It's quite not really that much to figure out. We can create a Q server, give it callbacks. You can connect as a client and deal with it purely asynchronously. So you can use coroutines, you can use futures, you can use callbacks, whatever you want. And it's all works quite easily. So that's one thing that we did. Also in the grab bag, now for something completely different. One of the problems that we run into frequently at Citadel Securities is we have these large tables that are keyed on multiple columns. And as some of you might know, this is kind of can be a tricky case in Q. There's only so much you can do. What are the options here? One is you can just kind of try to arrange the keys in a way that is most optimal and just kind of live with it. The other thing you can do frequently is sort of concatenate each column into a single string, turn that into a symbol, index based on that. You could use some kind of nested structure, i.e. not have one table, but have like a dictionary of tables. That's not really ideal. Sometimes it's nice to be able to just deal with things with a single table. The other option is convince yourself that you don't actually really need to do this. That's always the best option, sometimes not possible. So what did we do? We essentially implemented our own sort of homebrew attribute for this, where we will take the table, create a hash map, and essentially have a special set of functions to upsert into that table and use that hash map to do it efficiently. The hash map is basically just another vector of indices into the table. Again, so what you get with this is a significant improvement in performance. Again, this is going to depend very heavily on your data, properties of your data, but in general, it can be up to 10 times faster for certain things. Why is this in this talk about native code? It's because some C code is required. To essentially look up in that hash table quickly, you have to do an operation of find an index and then find the next element after that index that matches the table or that is null. And that's actually quite difficult to do in pure Q, in pure vector Q. Actually, I'm kind of laying this down as a challenge. If anybody can think of a way to do that in pure Q, please come talk to me afterwards. It sounds like it'd be fun. But for now, these are the C functions that we implemented to get this done. And as you can see, it works pretty well based on the previous slide. And that's about it. It's kind of a whirlwind tour of 2 projects that we did. I don't know if we have time for questions or we could save them for later. You could just hit me up afterwards.